Okay, so this section, obviously, I'm just adding whatever new interesting results are coming out that are of sufficient importance that I want to include them, even though this is an introductory course. So here we talk about a new paper that reports a new way in which it figured out whether the changes that occur during the glacial deglacial cycles in terms of CO2 had a fertilization effect on the terrestrial biosphere, which would mean it would have been a negative feedback. So if CO2 increases and terrestrial biosphere production increases, then it sequesters more carbon. So we have seen this before, the Vostok ice core record going back to 800,000 years. We looked at the temperature anomalies with respect to the base period. You have the rapid warming during the deglaciation and slow cooling during the glaciation and slow buildup of ice. So you have rapid release of CO2 by 80 to 100 ppm during the melting phase of the glaciers. Ice albedo feedback is positive in both directions, but it's slower here because as glaciers build, temperature cools, snowfall rates, atmosphere gets drier, snowfall rates slow down, so glaciers grow slower and slower. So you have a rapid melting phase, which is what we are in now with global warming, and the slow cooling phase, so rapid release of CO2 and slow decrease of CO2 of 80 to 100 ppm between deglacial times and glacial times. And the question the new paper tries to answer is whether this increase in CO2 would have led to increase in terrestrial biosphere and have acted as a negative feedback. And that's of course relevant to the current times as well, because we know that there is potentially some CO2 fertilization effect going on, but there are missing sinks, so often we don't have a good handle on where that missing carbon is going, and it's not easy to track the details of biospheric carbon sequestration to close the loop on many occasions. We have seen that in the plots we looked at for emissions coming from fossil fuels and land use, and the sinks in the ocean, land, and the accumulation in the atmosphere, and there are some leftovers which we call missing sinks. Karen Kofeld way back in 2007, I think, reported in Science the various hypotheses which are used to explain the drawdown of CO2 during glaciation, like ion fertilization. So glacial times have drier climate, more dust, more aeolian dust deposition on the oceans, which contains iron. So iron limited regions like the Southern Ocean, tropical Pacific, and so on can then have enhanced photosynthesis in the ocean and export more carbon. Or there could be whole ocean nutrient increase as well, which can then alleviate nutrient limitation and allow global increase in marine biomass and carbon export. Or nutrient utilization itself may become more efficient and remove CO2 from the atmosphere and export it to the deeper ocean. And there are other ideas like the rain ratio of calcium carbonate and organic carbon. So a decreased export of calcium carbonate relative to organic carbon from the surface to deep ocean maintains a high surface water alkalinity. So that makes CO2 more soluble into the ocean, and this would reduce deep ocean carbonate burial. Associated with the whole ocean alkalinity increase ends up drawing down atmospheric CO2. And then there is the silica leakage hypothesis where the diatoms in the Southern Ocean use less silicic acid relative to nitrate, so the excess silicic acid is exported to regions where it is needed, driving production and decreasing the calcium carbonate to organic carbon rain ratio. There are also ideas based on changes in sea level during glaciation, exposing more shelf areas, phosphorus availability, increased production, and so on. But just remember that when there are multiple hypotheses, it just generally means that we don't have a complete understanding of what is working, it's possible that all of them are working together, of course. Okay, so what is happening now with emissions from human activity increasing? We of course have the warming effect, which tends to reduce carbon storage on land and in the oceans. Oceans become less soluble with warmer waters absorbing less CO2. Of course, you also have ocean acidification impact, and oceans buffering ability decreases, and soil heterotrophic respiration increases with warming, so you have reduced carbon storage on land as well. On the other hand, if CO2 fertilization effect is working, then productivity and carbon storage would increase. There may be a threshold beyond which we may become much more in carbon sink source than a sink. Some of this may be already happening over the Amazon due to deforestation and warming as a whole. But during interglacial to glacial conditions, where you go from 280 to 300 ppm down to 200 ppm or so, orbital changes would start driving snow and ice increases. Slow cooling and glacier mass buildup would increase the carbon storage. We don't know where exactly, but we looked at the hypothesis for ocean storage. In atmospheric CO2 then decreases, which would drive to a gross primary production decrease on land, which would then increase CO2. So that's a the negative feedback to cooling, right? If you decrease atmospheric CO2, you would drive further cooling, but reducing atmospheric CO2, increasing atmospheric CO2 because of terrestrial biosphere accumulation going down, you would increase CO2. So is that what worked? So this paper in Science does some really interesting analysis looking at the oxygen-17 isotope. Typically, remember, we used O18 to do I won't go all the way back, to estimate temperature changes. So here there is a phase relation between CO2 and biospheric flux as recorded in oxygen-17 isotope, but this also depends on other processes like stratospheric tropospheric exchanges, so you have to worry about times when the two will be in phase and highly correlated like CO2 and oxygen-17, and times when this correlation is low, so there is non-stationarity in this. So they create a delta 17 in arbitrary units as shown here that removes the biospheric effect, so that you can look at the delta 17 offset with the biospheric or observed flux of the O17 versus this expected O17, and try to explain that in terms of the CO2 fertilization effect and increased biospheric production. So they do that with this time series here and look at the delta 17 offset over these 800,000 years, and they look at the 20,000 year moving correlation between CO2 and F17 or flux of C17, and you can see that the correlation can be negative, high and negative, can go to 0, and there are times when it is high and positive at the end of the so we are going back and going forward in time this way. So this is the end of the glaciation and beginning of the deglaciation, end of the deglaciation, beginning of the glaciation, and so on here. So the offsets between this expected delta 17 and observed delta 17 are used to argue that basically if you look at delta CO2 and gross primary production response in terms of the biospheric delta 17 response for various marine isotopic stages and various models including last glacial maximum, you can see that there is a very strong positive correlation between increased CO2 and increased gross primary production, confirming that in fact there was a very active negative feedback with the CO2 fertilization effect. There are also lead lag relations involved in terms of CO2 increase and biospheric response, which is consistent with the CO2 fertilization effect. They look at other details like the impact of glaciation in terms of the Dole effect, which looks at the ratio of O16 and O18 between the ocean and the atmosphere. Remember, glaciation creates a delta O18 response, and the temperature effects are also confounded in the O18. So they interpret the ITCZ shift northward and southward based on glacial deglacial times, which is also associated with sea level drop during glaciation and sea level rise during deglaciation. And of course, the key information here is in terms of the relation between the dust flux, weaker subantarctic zone ion fertilization and stronger subantarctic zone ion fertilization, and you can see that there is hardly any correlation there. The whole range of dust flux is basically not producing a significant relation with the gross primary production. So just take the message out of this that there is a CO2 fertilization effect that was definitely functional in natural variability during the Pleistocene, when glacial deglacial cycles occurred at the 100,000 year time scale. And this new technique of using O17 and the triple isotopic ratios allows them to conclude that terrestrial biospheric CO2 fertilization is a real intrinsic process of negative feedback in the system. As we said, we have to then see if this is still functional within the anthropogenic era or the Anthropocene, and whether that will continue to function as temperatures and CO2 increase, or at some point temperature effects will dominate in terms of driving CO2 outgassing from soil and reduced solubility in the ocean. Okay, so that remains, but the results are nonetheless very interesting that CO2 fertilization is a very strong part of the Earth system response to CO2 changes, driven by, of course, glacial deglacial cycles and orbital forcing in the Pleistocene, whereas now we are driving CO2 increase from fossil fuel burning and hoping that the CO2 fertilization of this terrestrial biosphere is drawing down some CO2. I'll come back and add another interesting podcast on how a newly found marine plankton is adding to carbon export in the ocean as well, with some unique predation strategies. It's a mixotroph, which means it can photosynthesize but also get some nutrients by doing heterotrophy or consuming other eukaryotic and prokaryotic particles, and that's an interesting new paper as well. Okay, so see you in the next podcast.